review sessions. And we are lucky to feature today Lisa McGaugh from Stillwater, Oklahoma, formerly from Northern Oklahoma College, an AP chemistry reader, NIMSY lead teacher from the Dallas-Fort Worth area. I'm Lou Akampora. I'm your host here, but Monique Rice also listening in as your real host. She knows what's going on. And we're looking forward to helping you answer some questions that you may see in about a month for the AP Chem exam. Just as we get started, please turn off your microphones or mute yourselves, turn off your student video, and feel free to use the chat room. This might be a good time to just introduce yourself. Where you're from is fine. We look forward to seeing all of you. And before I forget, this session will be archived on kyap2020.com, our website for teacher and student support. There are archives of other sessions and some supplemental resource material there. So before I turn it over, our presenter is Lisa McGaugh, Northern Oklahoma College retired, a NIMSY lead teacher, an AP chemistry question leader, and a close personal friend. Hi, Lisa. So I will turn it over to you. Lisa, unmute yourself. Lisa, you're muted. Always at a loss for words.
All right, there we go. Now, when you changed your screen, my screen also went away. And I was like, I'm not in Zoom anymore. Oh my gosh. All right, please be patient, students. Thank you for coming today. And I am going to share my screen. And we are going to look at a little bit of stoichiometry and reactions today. Do I think this would be your entire exam? No, I don't. But would it be part of your exam? Pretty sure. Because if they're going to just ask you 2 questions, then at least one of those questions is going to have to be something about reactions, and maybe something else has got to be about stoichiometry, right? I mean, that's kind of what we do as chemistry students and teachers. So let me just start this little PowerPoint, if it works that way, and it does. So we are looking at reactions in stoichiometry. I hope you have the packet downloaded. I hope you have this in front of you. If you don't, could you gather some supplies like your calculator, something to write with, periodic table, those would be all necessary things when we're talking about reactions in stoichiometry. I wanted you to see the equations that might be helpful when you're talking about reactions in stoichiometry. You know that this year you are in charge. You're in charge of supplying your own periodic table, your own equation sheet. So make sure that you gather those supplies. You still have a month. It's not really a hurry, but you do need to gather those supplies. There are a few other equations. You
probably know what they look like before the exam, so it wouldn't be terrible to be familiar with the equations.
True, true, true. And you can make yourself notes, guys, because you can have all of these things laid out in front of you this year. So that's going to be really unique. You could actually label, like you could say, oh, wait, this is my ideal gas equation, so this is for ideal gas. You could say, oh, this is when I'm going to do partial pressure. So you could put yourself little notes out here. That's what I would do. Like if I'm taking this test, I'm going to be writing myself some notes about when and where I'm supposed to do these things. So that's going to be one thing that you're going to be able to do. And that's going to be kind of nice, actually. If we look at the next slide, here are some equations that I would say, I said memorize, but really you don't have to memorize. You could just have this piece of paper out right beside you so that you would know what those kind of things are too, right? So percentages, College Board always thinks, well, that's a prior knowledge kind of statement. You learned percentages back in 7th grade when maybe you were doing math, right? So they don't really give you those formulas, but often that's going to come into play when you're doing some stoichiometry. The percent yield, like how much were you able to make out of what you should have made. Your error analysis, if you're doing any kind of a lab kind of question. And my gut is that lab question might be on this exam from looking at the description of the questions that were given to us a few weeks ago. Really, it looks like lab fits in very, very nicely because you could talk about all that error analysis. And then mass percent, maybe you would find a precipitate and you want to know the mass percent of a sample that was impure or something like that. And then empirical formula, and molecular formula, that always gets confusing too, because there's no formula to do that, but it's just getting the weights off the table. And so if you know the weight of the molar mass and the molar mass of the empirical formula, you can find a whole number ratio. And so we'll look at something like that today as we go through. So I just wanted to kind of point those out to you. You don't need to memorize them though. You do need to know what they're for and maybe have a practice example of each one. So the main types of reactions that you might encounter on this exam would be acid-base. How would you recognize acid-base? Well, if you look, you have to memorize, or I guess maybe you don't. That's so weird that you don't have to memorize these things. But an acid-base reaction, you have an acid in this reaction right here. In fact, you have HBr, which is a strong acid, and you have KOH, which is a strong base. It's really just double replacement like you learned in Chem 1. You make a salt and water. But you should be able to write those reactions. You should be able to write net ionic reactions from that. So we'll look at that in a second. Oxidation reduction reactions, how do you know those are redox reactions? Well, what you're searching for is you're looking for somebody in their elemental form probably. That's the easiest kind of oxidation reduction reaction. Like here, zinc has a charge of 0, but when you look at zinc chloride has a charge of 2+. And so zinc has gone from 0 to 2+. It has lost 2 electrons. Hydrogen from +1 to 0, hydrogen has gained an electron, right? No. Yes. Yes. All right. 0 to, yeah, +1 to 0. So you might be able to like actually identify those oxidation numbers. That would be a possible thing to do for a redox reaction that you might not be able to look up. A precipitation reaction, what you're looking for here, you have to know some solubility rules. So you see a solid that's formed when 2 aqueous solutions are mixed with each other. You do need to know that all group 1 cations are going to be, all of those salts are going to be soluble, and you should be able to use those to some extent on your exam. But again, I guess you could have all your solubility rules laying out beside you. You can't look everything up though in 45 minutes, guys. So, I mean, even though that's kind of like a little confidence, in your heart, you're going, okay, maybe I don't have to really know all this stuff, but you kind of do, because if you have to like search all your papers, you're going to take so much time, you won't be able to finish the exam. So you've got to know a little bit of stuff, right? So what kind of reactions might you have to do? You might have to do a balanced molecular reaction. That means a total balance with all of the formulas for all the compounds balanced, all the coefficients balanced. You don't have to worry about phases. I did put phases in here, but on the AP exam, traditionally, we've never scored those, whether you do it correctly or incorrectly. I still like to put them because it's going to make you get that kind of balancing thing right. The complete ionic equation, notice how this happens. So this is where my students always mess up. So this 3 coefficient goes for this whole compound. So 3 times copper gives me 3 copper 2 ions. You do have to know the charges. You leave off charges, we always leave off points, all right? So that's not fun. And then if you look at the nitrate as a polyatomic ion, so you kind of have to know those polyatomics. You have 2 of those, but you have 3 in front of the whole thing. So you really have 3 times 2 gives you 6 nitrate ions. And then following all the way across, 2 times 3 gives you 6 sodiums. 2 times this phosphate gives you 2 phosphate groups. On the product side, you have a 6 in front of sodium nitrate. So the 6 will go for the sodium and the 6 will go for the nitrate. And then you have a 3 subscript for copper. That subscript, but wait a minute. We don't ionize that, do we? Because when we do a complete ionic equation, we're going to just ionize only the things that are strong acids, strong bases, and soluble salts. So anything that's not very soluble will be a precipitate like that is right here. And if it's a weak acid or a weak base, we wouldn't ionize those. We would never ionize anything that would be liquid. So no ionization of liquids, all right, or gases, molecular compounds. So that's where those phases come in handy, because if I know the phase, then I'm going to be a little bit more honest with what I do. And then the net ionic equation, net is kind of like your net pay if you have a job. Maybe you get a gross pay and a net pay. A net is what's left over after they take all those taxes out, which is kind of sad. It's reduced to almost nothing, and that's what this net ionic equation is. So if you look at this net ionic equation, if you cancel out any spectators, here's a sodium ion, 6 of those with 6 of those. 6 sodium ions cancel with 6 sodium ions, and so all that's left, 3 coppers, 2 phosphates to make the precipitate copper 2 phosphate. And so that could appear in any kind of problem. We're only going to have 2, but I'm expecting students really don't do very well on these net ionic equations, so that's why I'm thinking that perhaps that might be something that you might see on your exam, because traditionally students have made mistakes kind of over and over. And again, if you leave off points, you leave off the charges, we have to leave off your points. And so reactions, did I just do that page? Here we go. Here's our first question for you, all right? So Mr. Akampora is gonna put up a little poll, and I want you to look at this. Does that poll box move a little bit, Lou? Yes, you can move it. I can move it around. So the question is, which box best represents the products for this reaction, and can you write the reaction? So check this out. See if you can actually tell me, the boxes are labeled A, B, C, and D at the bottom. So the reactants are in the initial box. The products are in the final box. This is a particular view of a reaction. So which one best represents the reaction that would take place here? And then can you write a reaction? So a couple of responses. Everybody try. This is totally, it's anonymous. Nobody knows.
Is anonymous.
Yeah, nobody knows. And then I'll work through it. So if you're wrong, that's okay, because if you're wrong, you're just going to learn something. I want you to know that this is a safe place. All right. This is a safe place. And so the more we study and hammer it out today, the better you're going to be when you take that test in a couple of weeks. Almost a month away, right? April, what's today?
Exactly
The 14th. Exactly a month away, May 14th. Yeah, May 14th. What time will it be in Kentucky when you take the test? 2? Because
yes,
it's
2
1.
o'clock.
Yeah, it's 1 where I am. All right, we've got a few more responses.
Okay, we'll give it 10 more seconds.
Okay.
So if you can eliminate 1 or 2, please just take a stab at the ones that you might not have eliminated. And we'll give you 3, 2, 1, and see what the results are.
Okay, so it looks like most everybody chose box A. So how would you choose box A? 9 people chose that. Does majority rule? Not really on the AP test, but that's okay. So let's check it out. So let's say, all right, so I'm going to move my poll box. Can I just like close it, Lou?
You can close it, Lisa. They won't see what you have.
Oh, okay. All right. So we have X2 and we have, whoops. Hey, go back. Previous screen. All right. So we have X2, gas. How do I know that's a gas? I'm asking that question. You don't really have to answer, but how would you know that that's a gas? Because that's when you look at these particle pictures, man. I mean, when I first started looking at these, this is not the way I was trained, and I was really confused. But look at the gas particles. They're everywhere in this container. They're not at the bottom. So a liquid would be at the bottom and not be really organized. A solid would be at the bottom and really organized, but a gas is going to be everywhere. So X2 is a gas and Y2 is a gas. And so what we make, it looks like almost in every container, we make a Y is the black one, the X is the clear one. And so we would have a Y, X3 gas, or you could say X3Y. Particle pictures don't know who's the cation or anion, don't know. So you just put it together however you want. And is that a balanced equation? Because that's really what you kind of have to do first. You guys were super fast at answering that. So here's what you really sort of have to do first. You have to have a balanced equation. So are we balanced? We have 2 X's, we have 3 X's, uh-oh. So let's skip that. Let's go to the Y's. There's 2 Y's, put a coefficient of 2 in front of Y, and that'll give you 2 Y's, and that will give you 6 X's. So I'm going to put a 3 in front of X2. And you guys, if I start going, I like chemistry a lot. And if I start going too fast and you're lost, Mr. Akapora is watching the chat and he can stop me and I can repeat or I can explain. And if my handwriting is so bad you can't read it, also tell him, say, hey, tell her to clean it up. I can't see the chat when I'm in this screen. So I don't know what you're saying out there, but please keep chatting. So now what I want to propose to you is that we might like actually count the particles. And I like to do these kind of things in just what I call rice tables. We're going to look at them again. We're going to look at them all the way through here. All right. I think they're super helpful for these little particle pictures. So if I count out how many X2s I started with 1, 2, 3, 4, 5, 6 X2s. And for Y2s, I started with 3. And I started with 0 amount of the product. So how many things could we actually make? We could use, who's going to limit? Does that look like a limiting reactant problem? Even though it doesn't have grams, it's okay. It is a limiting reactant problem, right? You know these from like Chem 1 also and from AP. So I'm going to go here. From every one Y2, you need 3 times as much X2, right? So if you have 3 of these, how many of these would you need? Wouldn't you need 9? You only have 6, so X2 is going to become my limiting reactant. I'm going to use all of them and be left with none. And then I'm going to say, okay, so if that's going to be my limiting reactant, I'm going to be left over with some of these. So what if we had 6 of these that we're going to use? We're going to use 6. How many of these would we actually use? For every one, you need 3 times as much. So if you had 1, you would need 3. If we use 2, we would use up 6 of those and we would be left with 1. And then if we go over here and do the same idea, look right here at this change row. So in this change row, we're going to lose 2 Y's, and for every 1 Y, you can make twice as much product. So if you're going to use 2, you could make 4. Do you see a picture that has 4 YX3s and 1 of the Y2s? And you guys were so on target because that would be choice A. And that's how I could prove that. But I could actually prove it with a particle picture and make it be pretty accessible even with particle pictures. So I don't know if that's how it might look on the exam. If Mr. Packer is thinking we can't just Google our answers, I'm thinking that that might be a possibility for how they could present us a limiting reactant problem where you could just use a 4-function calculator or even not need a calculator, right? Because those numbers were pretty easy to handle. Any questions about something like that? Lou, how's the chat box?
People seem to know what's going on here, Lisa, so keep going. You're doing great.
All right, so what is a mole? I know you guys have all seen this before, so I just wanted to put it up there again because this is another thing that I would probably lay out beside me just to make sure I don't do something in the wrong direction. When I get in that panic mode of 45 minutes, I might just have it as a glance, you know, I might just kind of like, oh, okay, I could look at this, but we can use moles to go every other place. The only thing I want to point out right here is I want you to be super duper careful about using that number right there, all right? When can you use that number? Only with a gas, and only with a gas at standard temperature and pressure. Do not get carried away with that number. We see that number being used over and over in an unlikely manner. So I just kind of showed you that rice table method, and you're going to have these, if you have this PowerPoint already, then you've got it in front of you. But you always have to have a balanced chemical equation if you're doing stoichiometry. It's always got to be there. And the I here, instead of, I know you guys probably just finished up equilibrium, the I in equilibrium stands for molarity. But in a rice table, when you're doing a reaction that goes to completion, that's going to be moles. And so you have to convert to moles before you put anything in that little table. And then C is for change. That's really going to go right with the coefficients. So C stands for coefficients in my book. All right. Because that's what guides the reaction. And then E is the ending moles. And then you can convert to whatever you need to convert to. So just a little introduction to that. Take a second and look at this equation. So in this equation, we have methane, the gas that comes out of the gas jets at school. They already tell us we have 1.5 moles of methane with 1.80 moles of oxygen. And it says assume that there's nothing of the products to begin with. And so I want you to look at two ice tables, and then we're going to do another poll because I want you to tell me which one makes most sense. So I want you to look at those two tables. We'll call this one table A, and we'll call this one table B. And so you just have a 50-50 chance to get this one correct. So Lou's going to put up a poll. Two votes. All right, come on, come on, come on. Yay.
There are a
It's a
lot of
50
numbers here, Lee, so let's give folks a good minute to assimilate all these numbers.
Yeah, actually, that is true. There's a lot of numbers there. That's what they're going to do to you on your AP test too, right? They give us a
Right.
table and they give us a million numbers and they're expecting us to read it in 7 minutes or something. Okay, somebody answered D. There is no D. There's only an A and a B. You can change your answer, I think. Can you change your answer
Yeah,
on
I
this
think you
one?
can change your answer. So
Until
whomever
he
changed
stops the
D,
polling.
and I'll give you 10 more seconds here. Maybe you can't change your answer. Okay, we've got most of the participants in, so let's see what the consensus is.
Consensus is choice B. You guys like that one the best? So let's look at this and see if it makes any sense. They both started with the same amount. So this row, hey, where's my pen? There it is. This row, those look exactly the same, right? So those rows look exactly the same. In this row, the assumption was that the methane is going to be the limiting reactant and you run out to 0. That's what will happen with a limiting reactant. It always runs out and it goes to 0 and then you have leftovers of the excess reagent. And so this one says for every for every one of these, you need twice as much oxygen, right? So if you had 1.5, you would need 3. So you would have to use 3 and you have to be left with a negative 1.2. Have you ever seen a reactant be smaller than it started off to be, like you lost it and it was in the negative range? I haven't. So that one is assuming the wrong limiting reactant. So when you look down at this next one, for every 1 methane, you need twice as much oxygen. So if you had that 1.5, you would need 3. You don't have that much. So you have to go backwards. You say we have 1.8. So about 2, we almost have 2, so it's going to be a little less than 1.5 over here, right? Can you kind of think of it in those terms? So we have a little less than 2, it's going to be less than 1.5. So 1.8, half of that is 0.9. You're going to have some leftover methane and you're going to have no oxygen left over. And then you use the ratios, to figure out these two products. So for every 1 methane, you can make 1 carbon dioxide. So if you're going to lose 0.9, you're going to make 0.9. For every 2 oxygens, you're going to make 2 waters. So if you're going to lose 1.8 moles, you're going to make 1.8 moles because their coefficients are exactly identical. I think that if we have easy numbers, these ice tables are going to make our problem solving super easy and not have to think really hard about dimensional analysis and get all of our numbers all mixed up. Because when you have this last line of moles, you can turn those moles into grams. You could turn them into liters if you had a gas at standard temperature and pressure. You could turn them into molecules or atoms or molarity. You could do all kinds of things with that mole. So that made a little sense. So now what I'd like for you to do is I would like for you to read this problem. This is a retired one. I bet you probably have already done it in class somewhere along the way. So what I would like for you to do is I would like for you to figure out the moles. So we've got 0.15 grams of lead 2 nitrate. We've got 125 milliliters of 0.1 molar sodium iodide. So what I would like for you to do is I would like for you to figure out the moles for each of these and see if you can determine which one you think is the limiting reactant. So we're going to call this one A for the limiting reactant. We're going to call this one B for the limiting reactant. And so, but I'm going to give you a minute to do that. And I'm going to just cheat for you. So I'm going to tell you the molar mass of lead 2 nitrate is 331 grams per mole. So you don't need to actually calculate that out, okay? You don't have to calculate that out, but you have to figure out the number of moles. So I want you to figure out the number of moles right there. And make sure that you show your work. To get a mole point, if you don't show your work, you get no points. So even though we have this nice little handy table, so you're calculating moles.
And it will be a small number.
Yeah, little bitty number. Because you're dividing a little bitty number by a really big number. 0.1 over 300 and something, that's crazy. So when you finish and you've kind of figured that out, maybe put a thumbs up or something. I don't know if you have that option in your chat box. Do you have that option in your chat box? It's on the Blackboard Collaborate. We have thumbs up that we can give on the chat box. Oh, I see thumbs up. Yes, yes, yes. I don't know why I only see Jacob and Emily and Chase on my sidebar. So are we ready to move? Lou, you want to put that poll and ask them who's the limiting reactant, A or B? See what they think. So you're just going to type in A or B, lead 2 nitrate or sodium iodide.
For the limiting reactant.
For the limiting reactant. Which one do you think is the limiting reactant? You guys are pretty fast.
And a few more seconds here. 3, 2, 1, and we'll see what we have.
All right. So look, guys, 70% of you said it was lead 2 nitrate. 30%, that's like 70-30. Awesome. 30% said it was the other one. So let's figure out how we actually do that. So here's what you would have to show minimum. I'm going to show you minimum work, okay? So you would have to, did it again. I'll touch it with my hand instead of my pen. Sorry, guys. Technology challenged, please forgive. All right, so 0.15 grams. And then I'm just going to say 1 mole over 331 grams. And when you divide that out, you do get a really, really small number over here. So if I set up my little ice table, that number comes out to be 4.53 times 10 to the -4th moles. You guys write a lot of digits. Don't just say 0.0004. Don't round that much because we started with 3 sig figs. At least give 3 sig figs if you have one of those teeny tiny numbers, because rounding too much could actually cost you a math error on the AP exam. Your answer could be very different. But this would be minimal amount of work, and then I could put my answer right there into my little ice chart, and I could get my mole point. So we don't have to see the whole calculation all the way through. I don't know how you deal with molarity and volume. My students really just like to go back into the formula that they're given on the equation sheet and plug in the molarity being 0.1 is equal to X over 0.125. You do not have to show conversion from milliliters to liters, but you would have to show this setup. And then that gives you a number that's actually pretty big in comparison to this number, because it's 1.25 times 10 to the negative 2 moles, and you started off with 0 and 0. So it should be choice A, because for every 1 lead nitrate, you need twice as much sodium iodide. Now, if you weren't being careful, you do have to look at this exponent. So check that exponent out first always, because 1.25 and 1.25 look smaller than 4.53, right? But you've got to be looking at the exponent to make sure that you're choosing the one that's the smallest. So we know what's going to happen here. And I know that you come on and do this little table with me, because I know you're going to feel the urge to fill in every blank just like I do. And I'm going to show you that when you do this, we can answer all the questions on the next page, basically. All right. So I would be left with nothing. Well, if I have to use twice as much sodium iodide as I do the lead 2 nitrate, that's going to be twice this number. So that's going to be minus 9.06 times 10 to the negative 4. And then I'm going to be left with 1.16 times 10 to the negative 2. All right, so let's go to our product side. We're looking for easy coefficients, remember? So I'm going to go up to my table and I'm going to say, okay, so there was 1 lead nitrate and there's 1 lead iodide. So if I'm going to use 4.53 times 10 to the negative 4th, then I'm going to make 4.53 times 10 to the negative 4th, and that's what I'm going to be left with, 4.53 times 10 to the minus 4th. I hope that's making some sense. Now, look at the sodium iodide. For every 2 sodium iodides, you're going to make 2 sodium nitrates. So if I'm going to use, always go to this C row, all right, that's the important row. If I'm going to use 9.06 times 10 to the minus 4, I'm going to make plus 9.06 times 10 to the minus 4. So I'm going to be left with 9.06 times 10 to the minus 4. This ending row is going to help me figure out so many things. It's going to help me figure out so many things you just don't know. I'm going to be able to answer almost all the questions on the next page. So have those numbers in front of you, all right? And let's look at the next page. Oh, that's where I was giving myself room to do it. I've already done it. List and part A, this part would not really be appropriate for our exam this year, because nobody's going to ask you, this is an old question from like 2008, I think is what it was. Yeah, 2008. So nobody's going to ask you to provide evidence of a chemical reaction between those 2 compounds. The answer there was that you make this yellow precipitate. You guys wouldn't have to know colors. And I guess you could say, well, there was a solid produced that the lead, the lead 2 iodide is a precipitate. You might be able to tell that because you know that iodides with lead are not going to be very soluble. So maybe that could be evidence. But look at part B. Did we calculate the moles of each reactant? Check. We did that. We would have gotten a point for that. I think it was 1 point, maybe 2. Identify the limiting reactant. You guys did that right after you calculated your moles, and you showed calculations to support. By doing the table, you showed the calculations to support, so we got all of that credit right. Now part D. Part D wants us to calculate the molar concentration of the nitrate in the mixture after the reaction is completed. So on part D, if we set up our molarity, we had 0.125 liters. Do you remember that? And then how many moles of nitrate did we have after the reaction was finished? If I go back, I think all of my writing might be gone. Oh, no, it's not. Okay, awesome. So if we look at this, we have 0 nitrate from over here on the reactant side. Do you see that? But on the product side, this is how much nitrate we have left over in solution, because Na and NO3, 1-to-1 ratio. So for every sodium ion, we make one nitrate ion. So this is my number, 9.06 times 10 to the negative fourth. So I even have what I need to find my concentration of my nitrate, because that's how many moles of NO3 minus. Now, if that had had a subscript 2, we would have to multiply it by 2, but we don't. So it's a 1-to-1 ratio. So we could get our molarity right there. And the concentration of that one comes out to be 7.25 times 10 to the minus third molar. How about that? And now what's even really, really cool is we can do this part with ease. So I want to go to the next screen, and I want you to choose the diagram by using that last row, the E row, the ending row. You can choose the diagram that best describes this reaction. So I'm going to label these, and you're going to make another poll, Lou, and we're going to say A, B, C, D, and E. Which image, looking at that final row that we had, which image actually best describes the reaction that we were dealing with right there? And that takes a minute too, just to kind of look, because there's lots of little particles all floating around. I'm thinking a particle picture like this would be a good option for the test because, you know, particulate representations are sort of big in AP, and they are big with stoichiometry. I could do them with equilibrium, so I could have particle pictures all over, but I wouldn't maybe expect you to have to draw one, but maybe pick one out from evidence that you've been given. And we were given evidence for this little experiment between lead nitrate and sodium iodide. And so maybe we would be able to pick out the particulate picture.
And because the AP Chem exam this year will be open note, open book, they're really trying to make it ungoogleable, if that's a word. So
right. That's what I was. So that's why I'm thinking this would be a good choice, right? Because you could Google this one particular question, but if they make a different question, you can't Google like a particle picture. That's why I was just thinking that might be a really good, maybe on track. I don't know, just thinking.
So if you can eliminate one or two of the choices, go ahead and take a guess. I'm going to end the polling in 3, 2, 1, and let's see what we have.
All right, so it looks like the majority chose letter C. And actually, I agree with the majority on letter C. So how do we figure that out? So let's see what we can eliminate right off the bat. We did have a precipitate, so this one has to disappear, all right? That one had no precipitate. This one has solid lead 2 nitrate. All nitrates are soluble, so that one's got to be wrong. So it really narrows it down to just 3 choices. All of these have solid PbI2. So this one has sodium, B has sodium and nitrate ions. The C even has some I- floating around and some sodium nitrate. And the D has some lead ions floating around. Well, let's go back really quickly and let's look at this table. Do we have any lead just floating around as an ion? We do not, right? We do not. We have some sodium nitrate. All this lead 2 iodide is the solid at the bottom of the beaker, but we had left over sodium iodide. So in our picture, we have to choose the one that's going to have some sodium and some iodide ions. And so you are exactly correct. If you chose C, that's the one you should have chosen. So that's exactly right. So that was a super not very accessible question when it was asked in 2008. But now with the power of doing those little rice tables, it's so easy. So yeah, do you like that? I'm excited about it. I hope that you're excited about it. So what I want you to do is I want you to try another one. Let's try another one. Here's from another AP exam. This time, this one is from kind of like a standpoint of, can you figure out what? I don't think they would actually make you draw the box, but again, they might have to make you figure out how to do it. Can you set up a rice table for this one and then predict what's going to be in the box on the left? Can you predict your own? Can you kind of set up a rice table and then predict your own?
And it looks like they've got to go backwards on this one because they're told what the
Product is. Yeah.
that is a product mixture. So a little
Yeah.
bit more challenging, but the same principles at work.
So we would have started with 0. We're trying to work backwards, and we only have a few givens, right? For NO2, we have, how many do we have? There's 1, 2, 3, 4. So if we had 0 and we ended with 4, the change must be a +4. Would you agree?
Yes, ma'am.
And then we're left over with 1, 2, 3, 4 of the NOs. So we have leftover NOs. Well, go back to your coefficients. That's the key. So for every 2 NO2s that form, you used 2 NOs. We know that we formed 4, so we must have used 4. So I'm going to go backwards and add, and 4 would give me 8. So I could draw 8 of these. You get the idea. I'm not such an artist, and you don't have to be either. And you don't even have to, you know what, if you line them up, actually, it makes it easier for us to grade because we can just count. So if you are ever doing one of these on another exam, there's my 8. So what about the oxygen? We don't have any left over. It was 0. Well, how does that work out right here with this change row? For every 2 NOs, you need 1 oxygen. So if we used 4 of these, how many oxygens would we have used? We must have used 2. So we must have started with 2. So we have to start with 2 oxygens. Isn't that easy? So that's only 1 point, but still actually that was 2. That was 2 points, Lou. That was 2, right?
That's
1
right.
for the right number of particles, and 1 if you actually got the particles drawn correctly, because some students just took these black and colorless, like they drew these instead of drawing these. So they didn't pay attention to the equation. And if they got the right number, we still gave a point, which was kind of crazy, but that's what we did. So that's how that works. So that was actually 2 points. So that's stoichiometry. Stoichiometry in the middle of a particle picture that you started at the end and you're trying to go backwards. And then think about all the ways that question could go maybe into equilibrium or all kinds of gas phase stuff. So let's try another one. I know you're having fun with this. I'm having so much fun with this. Oh my gosh, what is this? What is this? That's a titration curve, right? And you will be expected to do some stuff on a titration curve. So on a titration curve, you might actually have to figure out, you could figure out where the equivalence point is. That's going to be an expectation. So we have an acid. They didn't tell us what base. They just gave us an acid. That's a weak acid. And there's my base. You could do conjugate acid, conjugate base kind of stuff right there. That was in that unit 4. So we could be able to do conjugate acid, conjugate base. So weak acid, so this is my conjugate base. This is a base, so water in this case is acting like a conjugate acid. All right. Can you predict where is the equivalence point? So here's how our choices are going to go. Is it at A or B or C or D? So Mr. Akapor is going to put up another poll. Tell me where the equivalence point is. And just a little review of those titrations, you know that when the end point is where a color change might take place if you're using an indicator, and an equivalence point is really when the moles of acid equal the moles of base. So there's stoichiometry right there.
And we've got a pretty good consensus here, so I'm going to go ahead and end the polling.
Oh yeah, look at that. Awesome. Awesome, awesome. So you guys understand that idea, right? So equivalence is when this sharp line occurs. Then, since that's a weak acid and a strong base, you'll get to that when you get to college chem. This pH is somewhere in here, so it's above 7. It's not always going to be 7. We didn't talk about that yet for this exam, but that's the idea. So could you determine the initial concentration of the nitrous acid solution? That means I want the molarity in moles per liter. So how does that figure into this stoichiometry stuff? Well, the way that figures into the stoichiometry stuff, let's go to the next page. So I just have some space to write, okay? So if I wrote my equation, HNO2 plus OH minus goes to, did they give me NO2 minus and water? We start with nothing and nothing. So in our little table, sometimes we don't even have to finish the whole thing out to do what we want. At the equivalence point, we're going to have 0 of each of those. And so what we know is we had 0.1 molar KOH, and we know it takes 20 milliliters to get to that point. And from reading on the page before, we also know we have a 100 ml sample of this nitrous acid solution. So far, so good? So if that's what we know, we're going to have to kind of figure out, again, our moles. This is where we can figure out moles for the sodium hydroxide, or potassium hydroxide is what they gave me. So somewhere else on your paper, you're going to say 0.1 is equal to X over 0.002 liters, 0.02 liters, McGaw, right? 3 places to the left. So just 0.02 liters. And if I multiply 0.1 by 0.02, I'm going to get 0.002. I'm going to use all of that. And then you say, well, what's the ratio between the potassium hydroxide and the nitrous acid? It's a 1-to-1 ratio. So we're going to have to use 0.002, and that means I must have started with 0.002. Now I have all the numbers I need to find my molarity. The moles of nitrous acid are 0.002 moles. We started with 100 milliliters of that. And so I have my concentration being 0.02 molar. So stoichiometry can appear in all kinds of problems, I guess, is the big point. In fact, if we look at the next problem is even a different kind. So this is a redox kind of titration problem looking thing. It's an oxidation reduction, and it's a net ionic equation, and it looks freaking scary. Doesn't that look extremely scary? Yeah, completely scary. So the first question wants us to write a balanced half reaction for the oxidation of iron 2 to iron 3. That's still a fair question because redox reactions were covered in Unit 4. So let's write one of those. So if we go from iron 2 to iron 3, where are the there's only one electron that's different. Where is it? Is it a reactant or is it a product? Lou, I don't know. You want to skip that part? Skip that one?
Yeah, I think most people would get this one.
So if I write a symbol for an electron looks like E minus, right? That means electron has a negative charge. So we're not going to subtract an electron, but we add it, just like we would do if we were doing thermochemistry. So I'm going to put this electron right here. And so a -1 and a 3+ gives me 2+, matches 2+. That's a balanced half reaction. Now, if we look at letter E, what we have to do again is we have to do another stoichiometry table. And it just looks kind of scary, but it's not so scary. A student is going to titrate 10 milliliters of the iron 2. They want to calculate the value of they want the concentration. So it's just like what we did a minute ago, except the stoichiometry is not 1-to-1. And then we have weird numbers. Don't let strange numbers bother you. You have that many milliliters and you have 0.0350 molar. And so I think it's getting kind of close to time. So what I'm going to have you do is I want you to go and do this one by yourself, but just notice that this ratio is 1:5. So I know you know how to get the moles out of molarity and volume now. We've done that a couple of times. And then once you do that, you have your liters already right here. You can change those milliliters to liters and put them on the bottom, but the mole ratio is going to be for every one of these, you're going to have to multiply this by 5 to get the moles needed to get to the equivalence point in that particular titration. So that's going to be a little bit different, but it's not really, all right? It's not really different, except you've got to multiply by 5. So I want you to try that one on your own after you finish with this little session. And I want to just kind of run through just a couple more and ask you to try these also on your own, all right? But just kind of want to point out a couple of things. If you look at this one, look at this, I have a balanced equation. They tell me that we have a reaction at 120 in a rigid 25-liter container, and then we got a pressure at 0.4, and then they want to know the moles of Cl2. What in the world? So is an ice table going to come in handy? No, I have nothing. What is the magic formula that helps me when I want to get moles and I have a pressure, I have a volume, and I have a temperature? I know you're saying it in your head. You're saying it's I call it the pervert equation. It's not. It's called PV equals nRT. It's that ideal gas equation. So if I will say N is equal to PV over RT, please respect your algebra. That's what the most common mistake. Another common mistake is you got to change this temperature into Kelvin, right? So be sure you do that and pick out the right R. Write it down on your equation sheet. Which R do I use? If I'm using atmospheres, I'm going to use the R with atmospheres, 0.0821. So that's kind of a trick. So you're going to do that. And then on II, you can totally set up your rice table. All right. Because once you find the moles of the Cl2, then it says how many moles of this are needed. Well, you're just going to need 1/3 of them. And then you've got that one all over the place. And that one's going to be super easy. And then for after dinner tonight, this will be like your dessert, because now you have a fabulous stoichiometry problem to do that connects a lot of things, a data table. I'm thinking data table all over the place for this year. So what do you do with the data table? You respect those digits, all right? You respect those digits, because if we were going to do sig figs, which in my opinion, that's probably not a big picture item for this year when we only have 2 questions. But if we were doing sig figs, we would count exactly the number of sig figs, because you have to pay attention to the accuracy. And that's one of the things that it talks about in the question description for this year. So if we were doing that, I want you to be really respectful of those significant digits. Don't just leave anybody off. That's important. And then you've got some more information right here. An inert water, who cares about the filler? The tablet is dissolved in 50 mils of water. You have an excess of lead 2 nitrate. A yellow precipitate forms, filtered, washed, and dried. That would be a procedure that you might have to describe. The data is shown in this table. So they want a balanced net ionic equation, a net ionic equation. And why is the net ionic equation the best? Because like it shows me what's happening, right? All those spectators are left out. And then here's a good lab question. Why do you do the things you do in the laboratory? And then another question, really, really good down here, error analysis. I'm sure you are going to have an error analysis question. Well, I'm not sure. I haven't seen this test. But in my opinion, that would be a really good question to ask you about that. So your stoichiometry table can help you with this one. It can help you with this one. So you'll be able to answer all of those questions. Your teachers all have access to this. And I think, Lou, do they all have access to the answers too?
They can go to KYAP 2020 and it will be there by tomorrow, the answer key.
Okay, perfect. So that gives you tonight to do this for dessert, and then you can check it tomorrow. Does that sound fabulous? So I hope that this has helped a little bit of review, because stoichiometry was probably way back in August or September whenever you just began school, but it can be everywhere. So I would expect stoichiometry and reactions to be on this exam. So best of luck to all of you. Thank you so much for coming today.
Thank you, Lisa. And thank you, students and teachers, for participating. I wish you all luck and let us know how we can support you. We'll be signing off now. Bye-bye.
Thank you. Bye-bye.
Safe.